All right, so this is going to be a video about inverse trigonometric functions. Namely, we are going to be finding exact values of composite functions with inverse trig functions. So to kind of teach this concept, I basically have 4 problems here, many different flavors, many different trig functions on this. And the main thing that I do want you to notice as we're looking through these is like this one has an inverse sine and then a cosine inside of that inverse sine function. If you look at number 2, we have the inverse cosine with a sine inside of it. So all composite functions. And then 3, it kind of flips. The outside is just regular sine, and then inverse cosine is on the inside. And the last one, cosine, is on the outside, and then inverse tangent is on the inside. So it's all different combinations of these just to kind of show you how this works. By the end of this video, you should be able to find exact values of composite functions involving these inverse trig functions. So if you have any questions after this video, make sure you reach out to me and let me know. So we can just clarify that as much as possible. So let's dive in here. We'll start with number 1 here. All right, the first thing that you need to do here is, this is one big problem. We're gonna tackle just the smaller parts of this problem each bit by bit. So like this part right here, I'm gonna kind of tackle that first, and then we're gonna do the inverse sine of that. So we're gonna tackle this cosine of 13 pi over 6. So whenever you see a big problem, it's better to break it up into a bunch of sub-problems just to kind of help you get a better idea of how to solve this. Now, ideally, normally we've done these problems before in class. You've seen cosine of some value, and we're going to be looking at the unit circle to try to solve this. The problem with this is that 13 pi over 6 is not on the unit circle. It's too many times around the unit circle because the unit circle goes from 0 to 2 pi, and you can go around and around as much as you want, but it doesn't actually follow what's on the unit circle. That's kind of our home base. So we need to kind of get this to be a radian value, this 13 pi over 6. We need to get this to be a radian value that's actually on the unit circle so we can kind of figure out what this is. So to do that, we're over the 2 pi because 13 pi over 6 is over 2 pi. What we're going to do is we're going to subtract 2 pi on this. So you end up just going in a circle the other way. So we're going to subtract 2 pi from this. All right, just to kind of get a better idea of what we're looking at, I pasted a unit circle in here to kind of just to reference what we're looking at here. So if you look at the unit circle, we're going all the way around it to 2 pi, 0 to 2 pi this way. And that 13 pi over 6 is not on the unit circle, but if you subtract 2 pi from it, you're essentially subtracting 12 pi over 6 because 2 pi, if I wanted to, I can cross this out and write 12 pi over 6 since 2 pi is equal to that 12 pi over 6. So if you do that, now we end up with cosine of 13 pi over 6 minus 12 pi over 6. Well, that's just 1 pi over 6. And this value is actually on the unit circle. So pi over 6 is right here. The x value would be root 3 over 2. So cosine of that pi over 6 is equal to root 3 over 2. So what I can do is say this is equal to root 3 2. Now, all of this is in one big succession of equal signs, so that means that this root 3 over 2 is also equal to this cosine of 13 pi over 6, which is equal to this part right here that we started with. So now I can substitute that in to be the inverse sine of root 3 over 2. So I'm going to rewrite that real quick. So now we have the inverse sine of root 3 over 2. This big problem is now becoming a smaller problem because we solved that sub-problem in there of that cosine of 13 pi over 6. So what we're going to do is similar to kind of how we did this in class. We set this equal to theta, okay, because this is going to be some angle measurement. And if we sine both sides, you end up with root 3 over 2 is equal to sine theta. This is kind of our home base, and this is also equal to the y value on the unit circle. So we need to figure out where is the y value on the unit circle equal to root 3 over 2. So let's go back to the unit circle. We need to figure out where is the y value equal to root 3 over 2. And remember, you have to be in quadrants 1 and 4 for that inverse sine. So we're looking right here. We want root 3 over 2 as the y value, and that ends up being right here. So then the angle measurement is right there at pi over 3 for the final answer for this. The answer for this one would be the theta is equal to pi over 3, and that's our answer, so I'm highlighting it. So again, it's one big problem, but you're breaking it down into a bunch of sub-problems based on stuff that you already know. You know how to find the cosine of 13 pi over 6 because we did that in previous lessons. Now we're applying that when it's a composite function with that inverse trig. Okay, let's try this one over here now. Same kind of thing. We're going to start with that inner function, that inner part of the composite function, this part right here. Okay, so to do that, I'm just going to write sine of 11 pi over 4. Now, if you notice, this value is not on the unit circle. Okay, it's in the negatives. We go from 0 to 2 pi. So we need to figure out this value. To do that, we're going to add 2 pi this time. So we're going to go around in circles, but we're going around in circles by adding 2 pi. The other one we just did, we subtracted 2 pi. So this time we're going to add 2 pi. Now, when you do that, this 2 pi is actually just 8 pi over 4. I want common denominators with this 4 right here. So I did 8 pi over 4. But the problem with this one is that we still end up being in the negatives. So this ends up being equal to sine of negative 3 pi over 4. So what we need to do is add another 2 pi to this, which is essentially just adding another 8 pi over 4. And then we end up with sine of 5 pi over 4. Now, sine of 5 pi over 4 is on the unit circle. 5 pi over 4 is right here, and the sine value for that one is negative root 2 over 2. You want to look at the y value that's associated with that 5 pi over 4, because if you remember, sine on the unit circle is the y value. So this is actually going to be equal to negative root 2 over 2. So now that inner part of the composite expression is negative root 2 over 2, so that means this part right here is equal to negative root 2 over 2. So now what we're solving for is the inverse cosine of negative root 2 over 2. Now, if you remember, this is actually going to be equal to some angle measurement. If we cosine both sides, it kind of starts looking at like the problems that we're used to. Again, you don't have to do this step, but it just kind of helps me reorient myself. This is my home base. Cosine of something equals some value. And then this is the equal to the x value on the unit circle. So where is the x value equal to negative root 2 over 2? And if you remember, in cosine, it has to be in quadrants 1 or 2. So we want negative root 2 over 2. Negative root 2 over 2 is happening right here. And there's the angle measurement for it, 3 pi over 4. So we're going to go over here, and it solves for our theta value. So now our theta value is equal to 3 pi over 4, and that's our answer for this one. Okay, so cosine of 3 pi over 4 is equal to this negative root 2 over 2. We're looking for that theta value because this is the main problem that we're looking for in this whole problem. That's what the main thing that we're trying to solve for, is the very original inverse cosine of that sine of negative 11 pi over 4. So the answer to this one is 3 pi over 4. Let's go to number 3 now. Okay, now this one, it's a little trickier because we end up doing the inverse cosine of some fractional value, in this case 4/5, and the other one it's 5/12. So it's going to be a little bit different on this one, and you have to draw what I call a dummy triangle to kind of get an idea of what we're looking at here. Okay, so let's zoom in here so you can kind of see this a little bit better. Just like the last one, we're going to focus on the inner parts of this expression. So we're going to focus on this thing right here first. So I'm going to kind of just parse that out from the whole thing and just write inverse cosine of 4 over 5. Now, if you remember, inverse cosines are always equal to an angle measurement. So that's what we're looking at here. So I'm going to just set this equal to theta because theta is our variable that's used for angle measurements most times. We are going to, from here, cosine both sides. So then you end up with 4/5 is equal to cosine theta. Now we're going to use this to basically create a dummy triangle in which the cosine theta is equal to 4/5. It is important to note that your triangle does not need to be to scale. So I'm just going to draw a dummy triangle really quick. So we got a triangle here, connect the dots here. It has to be a right triangle because we're involving the trig functions here. And I'm going to say that my theta is this value right here, this angle right here. And then from here, the adjacent of this angle is 4, and the hypotenuse is 5. So I wrote 4 and 5 there because if you look at that, cosine theta is that 4 over 5. Now, we are looking for the sine of this angle. So if you notice right here, this theta right here represents this thing here, which also represents this thing here because they're all twins. So what we're really trying to find is sine of theta, because we solved that inner part to be equal to theta. So I can rewrite the original essentially to be looking like this, sine of theta. And that's what we're looking for on this, because I said this whole thing is equal to theta in the red step there. So if we're looking for sine of theta, and theta is based on this angle right here, it's basically going to be the opposite, whatever this thing is over here, over the hypotenuse. Well, this is a 3, 4, 5 triangle. If you want, you can use Pythagorean theorem to figure out what that opposite value is, but the value is going to be 5. Okay? I mean, I can do it really quick just to kind of show you. A squared plus B squared is equal to C squared. Our C squared is 25 because it's just this 5 squared right here. Okay, our base is that bottom one. That's 16 because it's 4 squared. And then we're looking for the A squared. I'm going to put that right there. You subtract off 16 on both sides, and you end up with A squared is equal to 9. You do the square root of both sides, and your A is equal to 3, which means this opposite is equal to 3, which your sine is the opposite over hypotenuse, so it'd be 3 over 5 for that trig ratio. And that's actually the answer for the entire problem. So if you notice the difference on this, I had to draw a dummy triangle. I mean, you don't have to, you can imagine that in your head, but it's way easier to draw out a dummy triangle. We didn't have to do that on the other ones because we were using the unit circle, which is based on all the triangles already, so that's why we didn't have to do that. But you do have to notice the difference in solving these. They are dramatically different. One involves triangles, one does not. So make sure you study this and understand that. And again, if you have any questions, make sure you let me know. All right, last one, same kind of thing. We're going to be starting with that most buried expression there, that inverse tan of 5/12. So I'm going to zoom in a little bit here. We can kind of set this all up. So the inverse tangent of 5/12. We're going to say this is equal to theta. Okay, inverse tangents always find the angle measurements. So that's what we're going to be doing first. From here, I'm going to tan both sides. So I'm going to write 5/12 is equal to tan theta. Okay, so from here, we're going to draw another dummy triangle to kind of get an idea of what we're looking at. So here's my triangle. Okay, it's a right triangle, and I'm going to put theta right here. So tan theta is going to be equal to the opposite over adjacent. In this case, it's going to be 5 over 12. Okay, but we are looking for cosine of this theta. Okay, just like last time, we're looking for cosine theta because theta is equal to this part right here, which is equal to this part up here. So we're just looking for cosine theta. Well, we have the triangle, so it's going to show us that it's going to be the adjacent, which is this 12, divided by whatever this hypotenuse is here. Okay, this is another Pythagorean triple, so I can just tell you right off the bat that the hypotenuse is 13, but I will leave it on you to do the Pythagorean theorem to prove it, but it should be a squared plus b squared equals c squared. If you work that all out, you should get that the hypotenuse is equal to 13. So now the cosine theta is pretty easy. It's just the adjacent over the hypotenuse, which is equal to 12 over 13. And that is the answer for the entire problem. So that's 4 basic examples kind of showing you how to simplify, how to find the exact values of these composite functions, knowing that they have inverse trig functions in there somewhere. Either they're on the outside or on the inside. Note that there is a difference in how I solved each of these. 1 and 2, I needed the unit circle, where 3 and 4, I had to make dummy triangles. If you have any questions about anything in this video, let me know.